All right, this week we discussed what still needs to be done for the project and how what we have been working on is going. So one of the obstacles that we're facing right now is accurately developing the transfer function. So if I share my screen here. So this is kind of the math going off of the provided bus suspension example. This is for our lunar lander shock absorber. The difference here is that the initial condition for our velocity is non-zero. And all the variables and stuff kind of stayed the same. What ended up happening is the only thing that was different is the force function U for like an actuator controller gets an additional velocity times the mass of the lander. And unfortunately, this kind of throws a wrench in the setup, as in the example, they have this matrix of the two different input functions, U and W. Well, there are some variables now with the addition of the non-zero initial condition that are independent of these inputs. So we're not really sure how to develop G1 and G2 based off of that. So we plan to talk to Dr. Fecamandi in the morning in his office hours. So that's one of the questions. Another thing we're wondering about is how to develop the functional diagram, since there are two input functions and also two equations of motion. So we're not exactly sure if we should try to somehow implement this all into one or do two functional diagrams. And we're not sure how that translates over to the block diagram either, if we want to develop one of those. And then we're not exactly sure what like the forcing function and the displacement function W are. If we want to use like impulse or step, or exactly how to develop those. But for the time being, as far as programming, Robert's got a program put together that uses an ODE solver instead of like transfer functions. That's putting out some pretty good results. So I'm going to let Robert start sharing and show some of the graph animations and stuff that came from that.
Yeah, let me pull it up here.
You need me to pause recording, or are you ready to go?
No, you just need to enable sharing or screen sharing.
There.
Okay, so here is my function. It's a modified Euler system for spring mass dampers that I had for numerical analysis. We're not all the way there. I haven't put Kole's equations in quite yet, but it has a general function of motion right here. And let's see if it'll pop up in the right screen. Of course it won't. All right, there we go. So here's I haven't labeled any of these, but this is our position to comet. And why does it keep doing that? And here is the velocity. So you can see it'll stabilize out at, I don't know, 0.06 or so. We got so far, and then here's just my actual plot that I was using. So this is where we're at, just generally. This is just for like the lunar lander landing on a hard surface, so we just need to change this function once we kind of finalize that and just put it in here. So
yeah, and that's something that we may need to change. Like if we don't get this stuff figured out, we could just consider it landing on a hard surface instead of having an additional spring and damper system, as in the bush suspension example, which they use for the wheel. They consider that as a spring and damper. We are going to consider the lunar regolith dust as a little mechanical absorption. I guess I can share that quickly. yeah, this system here. So this right here would be the regolith, and instead of having a bump that the wheel drives over, this W represents how like the compression of the soil, or the regolith, or the depth of it, I guess. So that's pretty much where we're at for this week. Like I said, we have a lot to talk about with Dr. Tekmandi in the morning. But does anybody else have anything to share for this meeting? All right, I'm going to stop recording then.